Alien oceans. Life in our solar system. For most of human history, the question of whether life exists beyond Earth was the stuff of myth and speculation. Ancient cultures imagined gods or spirits inhabiting the heavens, while philosophers wondered whether worlds without number might hold other beings like us. In the 20th century, that dream shifted into a scientific quest. We aimed our telescopes at Mars, Venus, and the Moon, searching for canals, clouds, and hints of alien greenery. But reality was harsher than imagination. When spacecraft arrived, the Moon proved to be a barren rock, Venus a crushing furnace, and Mars a cold desert. For a time, it seemed Earth might be the sole oasis in a lifeless solar system. But the story didn't end there. If the last century was about disappointment, this one has been about revelation. The farther our spacecraft travelled, the more we discovered that life's essential ingredient, liquid, may be widespread, not just on planets, but on moons. Not just on surfaces, but buried beneath ice, sprayed into space in geysers, or preserved in rocks and dust. In other words, the solar system is far wetter, and therefore potentially more habitable than we ever dared believe. The transformation began with Earth itself. For decades, biologists assumed that life required sunlight and temperate conditions. But the discovery of extremophiles, organisms thriving in boiling vents, acidic pools, radioactive mines, and the frozen depths of Antarctica, expanded our sense of what life can endure. If microbes can survive without sunlight, feeding on chemical energy in the darkest corners of Earth, then perhaps similar organisms could thrive in the hidden seas of icy moons or the fossil rivers of Mars. At the same time, planetary missions uncovered worlds stranger than we imagined. In 1979, Voyager passed Jupiter's moon Europa and revealed a cracked, icy crust, hinting at an ocean below. In 2005, Cassini at Saturn saw geysers spraying from Enceladus, proof of liquid water beneath ice. In 2005, the Huygens probe landed on Titan and photographed rivers and pebbles sculpted by methane rain. Meanwhile, Mars rovers traced the fingerprints of ancient water across the red planet. Even comets and asteroids, once thought inert, revealed organic molecules and water locked in their cores. What emerged was a new vision, the solar system not as a desert, but as an archipelago of possible habitats. Earth is not the lone island of habitability. It is one among many, perhaps the most visible, but not the only one, where life could gain a foothold. Each icy moon, each ancient river delta, each asteroid sample is a new port of call in the search for life. This shift carries profound consequences. For centuries, the search for alien life seemed impossibly remote, tied to distant stars and unreachable exoplanets. Now, the quest has come home. The nearest candidates for life are not light years away, but right here in our backyard, circling our own giant planets or orbiting within easy reach of spacecraft. If alien microbes exist in our solar system, they are within our grasp. And so the question becomes, where should we look first? Scientists have identified a shortlist of prime candidates. Europa, with its vast subsurface ocean, remains the most famous. Enceladus, spraying ocean material directly into space, may be the easiest to sample. Titan, with its methane seas and complex chemistry, offers an exotic twist. Mars, though dry today, preserves a record of ancient rivers and lakes that may still hide underground aquifers. Even the smallest wanderers, comets and asteroids, carry the raw materials of life, perhaps the very ingredients that seeded Earth. Each of these worlds tells a different story, but together they form a new narrative. That alien oceans are everywhere. They are not warm beaches under alien suns, but cold hidden seas beneath ice, or strange rivers of methane, flowing in eternal twilight. They may not look like Earth, but they could still host life. The task now is to explore. Missions are already en route or in planning. The Europa Clipper, set to launch in 2024, will fly past Jupiter's icy moon dozens of times. The Dragonfly drone, scheduled for launch in 2028, will leap across Titan's landscapes in the 2030s. Mars rovers, like Perseverance, are already collecting samples that will be returned to Earth. Proposals for future missions to Enceladus and other moons are gaining momentum. Each mission is a step closer to the ultimate goal, detecting life, or at least its traces beyond Earth. This chapter follows that journey. We will travel to Europa and its dark ocean, to Enceladus and its shimmering geysers, to Titan and its alien lakes, to Mars and its lost rivers, and even to the comets and asteroids that may have delivered life's ingredients. We will ask not only what these worlds contain, but what they mean, for science, for philosophy, and for our place in the cosmos. To search for life is to search for ourselves. In the icy moons and red deserts of our solar system, we may find answers that have haunted humanity for millennia. Are we alone? Or are the seas of life far wider than we ever imagined? Among the dozens of moons orbiting Jupiter, none captures the imagination like Europa. From afar, it looks like a pale marble streaked with fine cracks, as if someone had etched lines across a ball of ice. To the Voyager probes in 1979, it was a mystery. Cold, smooth, and oddly young compared to other scarred worlds. But by the 1990s, when the Galileo spacecraft entered orbit around Jupiter, Europa was revealed as one of the most intriguing places in the solar system. Beneath its frozen shell, scientists became convinced, lies a vast ocean. An ocean that may be one of the best places to look for life beyond Earth. Galileo's data transformed Europa from an icy curiosity into a world of possibility. Its images showed a surface unlike anything seen before. Great slabs of ice jumbled like broken pack ice on Earth's Arctic seas, long streaks where water seemed to have welled up and refrozen, and areas of chaos terrain where blocks of ice floated in a reddish matrix. These features hinted that Europa's surface was not rigid, but dynamic, moving over something softer. Perhaps liquid water below. Even more compelling was Galileo's measurement of Jupiter's magnetic field as it swept past Europa. The way the field was perturbed suggested that a conductive layer lurked beneath the crust. The simplest explanation? A salty, global ocean. Suddenly, Europa was not a frozen wasteland, but a water world, hidden beneath a shell of ice tens of kilometers thick. What makes Europa's ocean so fascinating is not just its size, larger in volume than all of Earth's oceans combined, but its potential to harbor life. On Earth, liquid water is the universal solvent, the stage where biology unfolds. If Europa has it in abundance, then the first requirement for life is met. But water alone is not enough. Life also needs energy. At Europa, that energy may come from below. Tidal forces from Jupiter's immense gravity flex the moon's interior, generating heat. That heat may drive hydrothermal vents on the ocean floor, just as on Earth's seafloor. Around such vents, where hot water rich in minerals gushes into the deep sea, ecosystems thrive without sunlight. Tube worms, clams, and microbes cluster in abundance, feeding on chemical reactions instead of photosynthesis. If such life can flourish here, why not in Europa's hidden seas? The ocean is sealed beneath ice in darkness, but that need not be a barrier. On Earth, microbes live miles below the surface in rocks and sediments, completely cut off from the sun. Extremophiles thrive in acidic pools, frozen permafrost, and the crushing pressure of the abyss. The discovery of such organisms has reshaped our definition of habitability and made Europa look less like a barren moon and more like a possible cradle of life. As if a buried ocean weren't tantalizing enough, evidence emerged that Europa may not be fully sealed. In 2012, astronomers using the Hubble Space Telescope detected what looked like plumes of water vapor spraying into space from Europa's south pole. Later reanalysis of Galileo data added support, showing signs that the spacecraft might have flown through such a plume unknowingly in the 1990s. If these plumes are real, they are a game changer. Instead of drilling through kilometers of ice to sample Europa's ocean, we could simply fly through the spray, capturing droplets as they vent into space. Already, scientists dream of missions that could taste Europa's ocean this way, analyzing its chemistry for salts, organic molecules, even biosignatures. It would be like dipping a straw into a hidden sea without breaking the surface. That dream is about to come closer to reality. In 2024, NASA will launch the Europa Clipper, a spacecraft designed specifically to investigate Europa. When it arrives in the early 2030s, it will perform dozens of close flybys, each time passing through Europa's environment, with a sophisticated suite of instruments. Clipper will carry ice-penetrating radar to measure the thickness of the crust and search for pockets of liquid water. It will use spectrometers to analyze surface chemistry, hunting for salts and organics. Its cameras will capture Europa's terrain in unprecedented detail, revealing fresh cracks, chaos regions, and possible plume sources. A dust analyzer will sample particles around the Moon, potentially catching evidence of subsurface material. Though Clipper will not land, its reconnaissance will be vital. It will tell us whether plumes are active, whether the ice is thin in some areas, and whether the ingredients for life are present. It will prepare the way for future missions that could land, drill, or even send submarines into the ocean below. Europa captures the imagination because it forces us to rethink where life can exist. For centuries, habitability was equated with Earth-like conditions, a planet in the habitable zone around a star, with surface oceans and sunlight. But Europa has none of these. It is far from the sun, locked in perpetual cold. Its surface is frozen solid, bathed in Jupiter's harsh radiation. Yet beneath the ice may lie a warm, salty ocean, teeming with chemical energy. If life exists there, even simple microbes, it would prove that biology is not a fluke. It would show that life emerges wherever conditions allow, even in darkness beneath ice. Such a discovery would ripple far beyond Europa. It would suggest that icy moons throughout the galaxy, of which there may be billions, could be alive. Life might not need Earth-like planets at all. It might thrive in hidden oceans everywhere. Europa also speaks to something deeper. To stand on its surface would be to stand above an ocean we cannot see, to know that below your feet lies a sea larger than Earth's, stretching in darkness for miles. The thought is humbling, and it reminds us that the most alien places may not be light years away, but orbiting just beyond Jupiter, waiting for us to listen to their secrets. For centuries, Enceladus was little more than a name in astronomical catalogues, a tiny icy moon of Saturn, overshadowed by its larger siblings like Titan. Barely 500 kilometers across, it seemed too small to matter, a frozen snowball orbiting in Saturn's rings. But in 2005, the Cassini spacecraft revealed a secret that transformed Enceladus into one of the most compelling places in the solar system. It was alive with activity, spraying geysers of water vapor and ice into space. When Cassini first flew past Enceladus, scientists expected little. Instead, cameras caught plumes erupting from the moon's south pole, fountains that rose hundreds of kilometers above the surface. These jets emerged from long, warm fractures in the ice, later nicknamed tiger stripes. Here was proof that Enceladus was not inert, but dynamic, heated internally, and connected to a reservoir of liquid water. Over the next decade, Cassini returned again and again. It flew directly through the Plumes, sampling their contents with onboard instruments. The findings were extraordinary. The jets contained water vapor, salts, silica grains, methane, carbon dioxide, and hydrogen gas, a chemical soup strikingly similar to the environments around Earth's hydrothermal vents. More than just water, Enceladus's plumes carried the ingredients for habitability. Early on, scientists wondered whether the plumes came from isolated pockets of water near the surface. But Cassini's data soon pointed to something much larger: a global ocean beneath Enceladus's icy shell. Gravity measurements revealed a wobble in the Moon's orbit that could only be explained by a liquid layer decoupling the crust from the rocky core. The chemistry of the plumes also suggested contact between water and rock deep below, just like Earth's ocean floors. This picture, a global ocean in contact with a rocky seafloor, heated by Saturn's tidal forces, was almost too good to be true. It meant Enceladus not only had water, but also energy and chemistry, the three pillars of habitability. On Earth, such conditions teem with microbial life. Could Enceladus host similar ecosystems, unseen beneath its crust, but betrayed by the geysers shooting into space? One of Cassini's most exciting discoveries came from tiny silica grains in the plumes. Their size and composition suggested they formed in hot water, perhaps as it bubbled through cracks in the ocean floor. In other words, Enceladus likely has hydrothermal vents, the very same kind of structures that sustain lush ecosystems at the bottom of Earth's oceans. The detection of molecular hydrogen added weight to the argument. On Earth, microbes called methanogens consume hydrogen and carbon dioxide, releasing methane. If similar microbes exist on Enceladus, they could be thriving in its dark ocean, feeding on the chemical gradients created by vents. Cassini didn't have the instruments to prove this, but the possibility electrified astrobiologists. Enceladus has one advantage that even Europa cannot match: it sprays its ocean into space. Sampling Europa's ocean may one day require drilling through kilometers of ice, but at Enceladus, the ocean comes to us. Cassini's flybys were proof of concept, but future missions could do much more. A dedicated spacecraft could fly through the plumes with instruments designed to detect amino acids, lipids, or even microbial cells. This makes Enceladus a uniquely accessible laboratory. It is as though the Moon itself is offering us samples, venting its secrets into space. To ignore such an invitation would be unthinkable. Astrobiologists have sketched bold proposals for exploring Enceladus further. One of the most exciting is the Enceladus Orbilander, a mission concept that would orbit the Moon for over a year, repeatedly flying through the plumes to gather data, before eventually landing on the surface. The orbiter phase would map plume activity and chemistry in unprecedented detail, while the lander would analyze fresh deposits of icy grains that have fallen back to the surface. Instruments could look for complex organics, isotopic signatures, or even direct evidence of biological activity. Though not yet funded, such a mission represents the future of exploration. A focused attempt not just to characterize a world, but to answer the question directly: is there life in Enceladus's ocean? Part of Enceladus's appeal is its sheer improbability. Who would expect such a small moon, so far from the sun, to be one of the most promising places for life? Yet its very smallness makes it more dynamic. Saturn's tidal grip keeps the Moon flexing and heating, its icy crust fractured, its ocean venting into space. There is also a beauty to Enceladus. Cassini's images, taken backlit against Saturn's rings, show plumes illuminated like delicate fountains, glittering against the blackness. In those fountains may lie the answer to one of humanity's greatest questions. Enceladus teaches us that habitability is not limited to planets or to the traditional habitable zone. It may thrive in the unlikeliest places. A frozen moon, smaller than Britain, orbiting in the outer darkness, yet alive with hidden seas. If we ever confirm life there, it would be a revelation. It would show that life does not require Earth-like conditions, only the right chemistry and energy. It would suggest that across the galaxy, icy moons and ocean worlds could be alive with microbial life, unseen but abundant. Enceladus, tiny though it is, could unlock the cosmic truth that we are not alone. Among Saturn's 145 known moons, Titan stands apart as a world that seems strangely familiar and utterly alien all at once. Larger than Mercury, and wrapped in a thick orange haze, Titan has an atmosphere denser than Earth's, and landscapes that, from a distance, could be mistaken for our own. But step closer, and the resemblance twists. Its rivers and lakes are not filled with water, but with liquid methane and ethane, flowing and evaporating in a cycle eerily parallel to Earth's water cycle. For centuries, Titan was an enigma. Its dense atmosphere, rich in nitrogen, hid the surface from telescopes. The first real glimpse came in 2005, when the Huygens probe, built by the European Space Agency, detached from the Cassini spacecraft and parachuted through Titan's haze. The images it sent back were astonishing. Rounded rocks strewn across a floodplain, carved channels that spoke of flowing liquid, and a dim orange sky arching over an alien landscape. Huygens survived only a few hours on Titan's frigid surface, where temperatures plunged to minus 290 degrees Fahrenheit, minus 179 degrees Celsius. But its data confirmed what scientists had long suspected. Titan was not static, but dynamic, shaped by processes reminiscent of Earth's. Cassini's radar soon mapped the poles, revealing sprawling lakes and seas of liquid hydrocarbons, some as large as the Great Lakes of North America. The largest, Kraken Mare, covers an area larger than the Caspian Sea. For the first time, humanity had found another world with stable liquid on its surface. Titan's methane cycle, clouds, rain, rivers, lakes, and evaporation, mirrors our own hydrological cycle, only colder and stranger. What does this mean for life? On Earth, water is the universal solvent, the stage for all biology. On Titan, water is locked up as rock-hard ice, while methane and ethane flow as liquid. Could these hydrocarbons play the same role? Some scientists suggest that in Titan's seas, exotic methane-based life could exist, with cell membranes built not from lipids like ours, but from molecules adapted to cold, non-polar solvents. In laboratory simulations, researchers have shown that azotosomes, flexible, cell-like structures made from nitrogen compounds abundant on Titan, could theoretically form and function. Even if Titan lacks such alien biology, its chemistry is invaluable. The thick atmosphere is rich in organic molecules, including nitriles and hydrocarbons that rain down onto the surface. These are the same kinds of compounds that likely filled Earth's skies before life began. Titan, in this sense, is a laboratory of prebiotic chemistry, a frozen echo of our own early planet. By studying Titan, we study the possible pathways by which lifeless chemistry crosses into living complexity. Yet methane seas are not Titan's only secret. Gravity data from Cassini strongly suggests that beneath Titan's icy crust lies a deep subsurface ocean of liquid water mixed with ammonia. This makes Titan doubly intriguing. A world with two oceans, one exotic and hydrocarbon-based on the surface, and one water-based and potentially habitable below. No other moon offers such duality. The surface seas may show us how alien chemistry operates, while the hidden ocean might harbour conditions more familiar to terrestrial biology. The next leap in Titan exploration will come with NASA's Dragonfly mission, scheduled to launch in 2028 and arrive in the mid-2030s. Dragonfly is unlike any mission before it. A nuclear-powered, 8-rotor drone, capable of flying tens of kilometers at a time across Titan's varied landscapes. Unlike rovers limited to crawling, Dragonfly will soar over dunes, plains, and possibly even lake shores, sampling multiple sites in a single mission. It will carry instruments to analyze organic molecules, search for prebiotic chemistry, and measure the surface environment. Its mobility will allow it to compare regions shaped by different processes, from atmospheric rain to possible cryovolcanism. Dragonfly's target landing site, the Shangri-La dune fields near the equator, offers a diverse environment rich in organic material. From there, the drone will hop toward the Selk impact crater, a site where water and organics may have once mixed. Scientists hope this journey will reveal not only Titan's chemistry, but whether conditions for life, methane-based or water-based, could exist. Titan challenges our assumptions about habitability. It tells us that life might not require Earth-like warmth or even water on the surface. It may emerge in seas of methane, in temperatures cold enough to freeze steel. Even if Titan turns out to be lifeless, it still serves as a natural experiment, showing how complex organic chemistry unfolds in alien conditions. Philosophically, Titan also expands the imagination. To stand on its surface, surrounded by dim orange light, methane clouds drifting overhead, and lakes stretching into the haze, would be to experience a landscape both familiar and profoundly alien. It forces us to confront the possibility that life, if it exists elsewhere, may not look anything like us. It may not breathe oxygen, drink water, or build with carbon the way we do. Yet it would still be life, proof that the universe's creativity far exceeds our own. Cassini's final images of Titan, backlit against Saturn's rings, captured the moon glowing softly in the darkness. It looked like a lantern hanging in the void, its thick haze hiding mysteries we are only beginning to understand. Beneath that haze are seas that lap against icy shores, rainstorms that carve river valleys, and a chemistry that may echo the first sparks of life. In the coming decades, when Dragonfly's rotors buzz through Titan's skies, humanity will finally touch this world more deeply. Whether it reveals methane-based microbes, prebiotic chemistry, or simply a stunning diversity of alien geology, Titan will remind us that the solar system is stranger, richer, and more alive with possibility than we ever dreamed. If Europa and Enceladus invite us to imagine oceans hidden under ice, Mars invites us to imagine oceans that once were. Today, the red planet is cold, dry, and dusty. A world of dust storms, frozen poles, and a thin atmosphere barely able to cling to carbon dioxide. Its landscape is a desert of rocks and craters. And yet, everywhere we look, there are fingerprints of water. Billions of years ago, Mars was warmer and wetter. Gigantic valleys like Valles Marineris speak of massive tectonic rifts where water may once have pooled. Ancient river channels snake across the surface, winding and branching in patterns that look unmistakably like streams on Earth. Orbital images show fans and deltas, where rivers once spread their sediments into lakes. Minerals like clays and sulfates, which only form in liquid water, are scattered across the Martian crust. Some scientists believe Mars once had a northern ocean, covering much of the planet's lowlands. If true, this would have made Mars a truly Earth-like world. Blue skies, seas, rivers, and a climate capable of sustaining them. For perhaps hundreds of millions of years, Mars may have been not just habitable, but inhabited, But Mars was too small to hold on to this paradise. With only about 38% of Earth's gravity, it struggled to maintain a thick atmosphere. Around 4 billion years ago, as Mars's molten core cooled, its global magnetic field faded. Without that protective shield, the solar wind began stripping the atmosphere away. Over time, Mars lost most of its air, its pressure dropped, and its climate collapsed. Surface water evaporated or froze, leaving behind dry basins and ice locked underground. What we see today is the fossil of a once vibrant world, a desert etched with the scars of rivers and lakes long gone. Yet in those fossils lies hope. Because if Mars once hosted water, then it may once have hosted life. And traces of that life, if they exist, could still be preserved. Our understanding of Mars's watery history comes from decades of robotic explorers. The Viking landers in the 1970s were the first to look for life directly, with inconclusive results. Later, the Spirit and Opportunity rovers in the 2000s found compelling evidence of ancient lakes and groundwater. Opportunity discovered hematite blueberries, small mineral spheres that form in watery conditions. Spirit, climbing a hill in Gusev crater, uncovered rocks altered by past hydrothermal activity. Then came Curiosity, landing in Gale crater in 2012. Its instruments drilled into rocks that once lay at the bottom of a lake, finding clays and organic molecules. Curiosity confirmed that Gale crater had once been a habitable environment, a place with water, energy sources, and carbon chemistry. Today, Perseverance rover, which landed in Jezero crater in 2021, is pushing this quest further. Jezero was once home to a river delta, a perfect environment for preserving organic material. On Earth, river deltas are rich in fossils because they trap sediments and protect them from erosion. Perseverance is exploring Jezero with a suite of instruments: Sherlock for detecting organics, Pixel for analyzing chemistry, and SuperCam for remote sensing. More importantly, Perseverance is drilling and caching samples in titanium tubes, the first step in the ambitious Mars sample return mission. In the early 2030s, NASA and ESA plan to launch missions that will collect Perseverance's sample tubes and bring them back to Earth. This would mark the first time humanity has retrieved material from another planet. With these samples in Earth's laboratories, we could search for biosignatures, organic molecules, isotopic ratios, or even fossilized microbial shapes, with precision far beyond what rovers can achieve. If even one tube contains evidence of past life, the implications would be staggering. It would prove that life emerged twice in one solar system, and if it happened twice here, it could happen countless times across the galaxy. Mars also holds a more immediate puzzle: methane in its atmosphere. Trace amounts of methane have been detected by orbiters and rovers, sometimes fluctuating seasonally. On Earth, most methane comes from biology, microbes breaking down organic matter, though it can also arise from geology. On Mars, the source remains uncertain. Does it seep from underground reservoirs, produced by geological reactions? Or is it the exhaust of microbial ecosystems hidden below the surface? The question remains unresolved, but it keeps Mars in the spotlight as a possible host of current, not just ancient life. Even if Mars's surface is hostile today, underground may be different. Beneath the shielding of rock and ice, aquifers could persist. Radar data from Mars Express has hinted at possible briny lakes beneath the South Polar Cap, though the interpretation is debated. If microbes survive anywhere on Mars, it may be in these hidden refuges, thriving on chemical energy far from the sun's rays. Earth provides analogues: bacteria living miles underground in deep mines, or in subglacial lakes beneath Antarctica, isolated for millions of years, yet still alive. Such examples remind us that life is tenacious, and Mars, even now, may harbour it. Another possibility ties our two worlds even closer. Rocks from Mars frequently land on Earth, blasted off by asteroid impacts and drifting through space before crashing here. Martian meteorites have been found in Antarctica and deserts, identifiable by their chemistry. If life existed on Mars billions of years ago, could microbes have hitchhiked on such rocks and seeded Earth? Or vice versa, with Earth microbes colonizing Mars? This idea, Panspermia, suggests Earth and Mars may not be isolated experiments, but connected laboratories. If life is found on Mars, determining whether it is independent or related to Earth will be one of the great scientific quests of the century. Mars may not have oceans today, but its memory of them makes it one of the most important worlds in the search for life. It offers a test of whether life can arise wherever water once flowed. It also offers the most accessible stage for humans. Within decades, astronauts may walk its dusty plains, drill its rocks, and search firsthand for signs of life. Mars is a paradox. On the surface it looks dead, yet beneath its rocks may lie traces of vitality. It is barren today, yet once may have been blue. It is near enough for us to reach, yet mysterious enough to keep us guessing. More than any other world, Mars tells us that oceans are not always eternal, that they can vanish, leaving behind fossils in stone and whispers in the air. To explore Mars is to explore a mirror of Earth's past, a possible future of planetary decline, and perhaps a record of a second genesis. If that record exists, it lies waiting in the river deltas, in the samples. Perseverance is caching, in the methane drifting faintly through thin skies. And if we find it, we will know. Life is not unique to Earth. The cosmos itself is fertile. Would you like me to continue straight into section 6.6? Comets and asteroids, couriers of life for the next approximately 1,500 words? If Europa and Enceladus stir our imaginations with hidden seas, and Mars tempts us with rivers long gone, then comets and asteroids remind us of life's most basic story, how it began. These small ancient wanderers of the solar system are not worlds in the conventional sense. They are fragments, rubble left over from the solar system's birth 4.5 billion years ago. Yet in their primitive chemistry may lie the answer to one of humanity's oldest questions. Where did the ingredients of life come from? Comets and asteroids are often called time capsules. Unlike planets, which underwent violent heating, differentiation, and geological recycling, many small bodies have remained relatively unchanged since the earliest days. Locked in their ices and minerals are records of the chemistry that swirled in the protoplanetary disk around the young sun. To study them is to peek into the recipe book of the solar system's creation. And the recipe, it turns out, is surprisingly rich. Meteorites that fall to Earth, fragments of asteroids that survive the plunge through the atmosphere, have long been known to contain organic compounds. Some harbour amino acids, the very building blocks of proteins. Others contain sugars and nucleobases, ingredients of RNA and DNA. These are not contaminants from Earth. They are extraterrestrial, forged in the cold chemistry of space. If such molecules rained down on the early Earth, they could have seeded the primordial soup with the raw materials needed for life to emerge. Among asteroids, the most intriguing are the carbonaceous chondrites, dark, carbon-rich bodies that preserve water-bearing minerals and organics. Famous meteorites like the Murchison fall in Australia, 1969, astonished scientists when analysis revealed over 70 kinds of amino acids, including some not used by life on Earth. It was a dramatic demonstration that the chemistry of life is not unique to our planet. It is written into the cosmos itself, but meteorites are only fragments. To truly understand these bodies, we needed to visit them. In the 21st century, space agencies began mounting bold missions to bring asteroid material directly to Earth. Japan's Hayabusa mission was the first, returning tiny grains from asteroid Itokawa in 2010. Its successor, Hayabusa 2, targeted Ryugu, a diamond-shaped carbonaceous asteroid. In 2020, it delivered pristine samples back to Earth, including amino acids and organic material. Meanwhile, NASA's OSIRIS-REx traveled to asteroid Bennu, a near-Earth object only half a kilometer wide, but thought to be rich in carbon compounds. In 2020, it performed a daring touch-and-go maneuver, kicking up a cloud of dust and capturing a sample in its collector head. In 2023, that sample parachuted to Earth, the largest collection of asteroid material ever delivered. Early analysis confirmed the presence of organic molecules and hints of hydrated minerals, supporting the idea that Bennu's parent body once carried water. These missions show that the seeds of life, amino acids, carbon compounds, perhaps even complex organics, are not rare, but widespread among the solar system's debris. Asteroids are not alone in this role. Comets, icy bodies from the outer solar system, are also prime couriers of life's ingredients. When comets approach the Sun, their ices sublimate, releasing gas and dust into a glowing coma and tail. For centuries, comets were viewed as omens. Today, they are viewed as laboratories. One of the most remarkable explorations was the Rosetta mission, launched by the European Space Agency. In 2014, Rosetta arrived at Comet 67 P/Churyumov-Gerasimenko and orbited it for 2 years. Its lander Philae bounced to an awkward resting place, but still returned data. Instruments detected glycine, the simplest amino acid, along with phosphorus, a vital ingredient in DNA, ATP, and cell membranes. This was direct confirmation that comets carry not just water, but the very molecules central to biology. Comets may also have delivered much of Earth's water. The isotopic ratio of deuterium to hydrogen, DH, in cometary ice provides clues. Some comets match Earth's oceans, suggesting they contributed to filling our seas. Others differ, pointing to asteroids as the dominant source. Either way, small bodies seem to have played a critical role in Earth's hydration. If comets and asteroids delivered organics, could they have delivered life itself? This is the bold idea of panspermia, that microbes could survive ejection from a planet, endure the harshness of space within rocks or ice, and seed another world upon impact. Laboratory experiments show that some hardy microbes can indeed survive extreme cold, vacuum, and radiation for long periods. Whether any actually made the journey is uncertain, but the possibility adds drama to the story. If true, then life may not have begun independently on Earth at all, but arrived as a traveller from Mars or beyond, carried on a cosmic courier. In that case, life might be a galactic hitchhiker spreading wherever conditions allow. It is easy to overlook comets and asteroids, given their size. They lack atmospheres, oceans, or landscapes like the great planets and moons. Yet in a sense, they are more fundamental. They are the source material from which planets were built, the couriers that delivered water and organics, the storytellers of the solar system's earliest days. And their relevance is not just in the past. Today we continue to study meteorites that fall, comets that pass, and samples returned by spacecraft. Each adds detail to the tapestry of life's origins. They are also practical. If humans venture into deep space, asteroids may serve as fuel depots or resources. But perhaps their greatest gift will remain their role as messengers, carriers of the molecules that hint that life's potential is written into the universe itself. We often say we are made of stardust, forged from elements created in stars. But we are also, in a very real sense, made of comets and asteroids. The water in our cells may once have frozen in a comet's heart. The carbon in our DNA may have formed in the cold chemistry of an asteroid. To study these small bodies is to study ourselves at the deepest level. In their icy grains and dusty pebbles lie the beginning of the story that ends in oceans, forests, and human beings. In their chemistry lies the promise that the universe, given time, tends toward life. The phrase alien oceans stirs images of distant exoplanets orbiting foreign suns. But perhaps the most astonishing truth of modern exploration is that such oceans are already here, close to us, hidden within our own solar system. Each new mission has revealed that water, once thought rare beyond Earth, is abundant. And not just water, but energy and organic chemistry, the ingredients of habitability. Taken together, these discoveries point to a startling possibility. Our solar system may host multiple potential habitats for life, scattered like pearls in the dark. From Europa's buried ocean to Enceladus's spraying geysers, from Titan's methane seas to Mars's ancient riverbeds, from the organics in asteroids to the icy ices of comets, each tells us the same story. Life might not be confined to Earth. For centuries, habitability was defined narrowly. A world had to be Earth-like, orbiting in the habitable zone where liquid water could exist on the surface, with a temperate climate and a protective atmosphere. But the discoveries of the last 50 years have shattered that neat box. Europa shows that oceans can exist under ice, heated not by sunlight, but by tidal forces. Enceladus demonstrates that such oceans can vent material into space, making them accessible for study. Titan proves that liquid can exist in forms other than water, with methane and ethane carving landscapes under a dense atmosphere. Mars shows that habitability can be temporary, that worlds can shift from blue to red, preserving fossils of their past. Comets and asteroids remind us that habitability begins with chemistry, scattered through the cosmos in the smallest bodies. Habitability is no longer a simple zone around a star. It is a spectrum, defined by the interplay of water, chemistry, and energy, no matter how strange the context. Perhaps the most profound revelation has been the recognition that life does not need sunlight. On Earth, we once assumed the sun was the ultimate source of energy. Then, in the late 1970s, explorers of the deep ocean discovered hydrothermal vent ecosystems. Thriving communities of microbes, worms, and clams, all living in total darkness, feeding on the chemical energy released by hot fluids from the sea floor. Here, life builds entire ecosystems without a single photon of sunlight. This discovery reshaped astrobiology. If life can thrive without the sun, then it can thrive beneath ice, beneath rock, in oceans sealed off from the sky. Europa's vents could host microbial communities, like those in Earth's abyss. Enceladus's hydrogen-rich plumes suggest similar chemistry at its seafloor. Even Titan's icy ocean, buried below hydrocarbons, may harbour chemical gradients to feed life. In this new vision, habitability is not fragile but resilient. Life does not require Edenic conditions. It requires niches, cracks, where energy and chemistry meet. The solar system is filled with such niches. Titan challenges us further by asking whether life must even use water. Could methane or ethane serve as solvents? Could cell membranes form from exotic molecules in Titan's seas? On Earth, all life is built on the same template: DNA, proteins, lipids, water. But Titan whispers that this template may not be universal. Life could be more diverse, more adaptable, more alien than we can imagine. Laboratory simulations on Earth have shown that flexible, cell-like structures called azotosomes could form in liquid methane, using compounds abundant on Titan. While no one knows if such life exists, the thought alone expands biology into new territory. Life might not just adapt to different conditions. It might reinvent itself entirely, given a different chemical canvas. If Dragonfly finds even hints of self-organizing chemistry, Titan will remind us that life is not a narrow pattern, but a principle. A tendency of matter to organize, adapt, and persist wherever conditions allow. Mars teaches a different lesson. It tells us that habitability can be fleeting. For hundreds of millions of years, Mars may have been as friendly to life as Earth, with rivers, lakes, and perhaps an ocean. Then it lost its atmosphere, and with it its surface water. Yet in its rocks, Mars may still preserve the record of those early days. Perseverance's samples from Jezero crater could one day confirm that life emerged there. If they do, we will know that life arose twice in one solar system. That would be one of the most profound discoveries in history. Even if no evidence is found, Mars remains a cautionary tale. It reminds us that planets change, oceans vanish, atmospheres can be lost. If life is fragile, we must protect our own world, not only for ourselves, but for the universe that may be watching. While moons and planets host oceans, comets and asteroids may have delivered the ingredients. Meteorites on Earth show amino acids, sugars, and even nucleobases. Rosetta found glycine and phosphorus on a comet. OSIRIS-REx and Hayabusa. Two returned asteroid samples rich in organics. The implication is clear. The building blocks of life are not rare. They are scattered through space, formed naturally in the cold chemistry of the cosmos. Any world with water and energy may be stocked with the raw material for biology. Life may not require rare miracles, but only time. Some even suggest panspermia, that life itself may travel between worlds on rocks ejected by impacts. Earth and Mars may already share biology, exchanging microbes over eons. If true, then life is not just possible elsewhere. It may already be seeded throughout the solar system. When we ask whether alien oceans could host life, we often turn to Earth's extremophiles for guidance. On our planet, microbes thrive in boiling acidic springs, in frozen glaciers, in radioactive caves, in brine pools saturated with salt. They endure crushing pressure miles below the ocean, and vacuum conditions in the upper atmosphere. Some survive exposure to the vacuum of space itself. These organisms show that life is astonishingly adaptable. If it can thrive in such extremes here, it could thrive in Europa's ocean, in Enceladus's vents, in Titan's lakes, in Martian aquifers. Earth's biosphere is not an exception, but a demonstration of resilience. Viewed this way, our solar system resembles an archipelago of oceans. Earth is the central island, rich with life. Europa and Enceladus are neighboring isles, their seas hidden but deep. Titan is a strange island, with methane rivers and a buried water sea. Mars is an island of memory, where rivers once flowed. Comets and asteroids are couriers sailing between islands, carrying the seeds of life. This archipelago metaphor reshapes our perspective. We are not alone on a single oasis. We are surrounded by a chain of potential habitats, each awaiting exploration. The search for life is no longer only about distant stars, but about understanding the seas in our own backyard. The next generation of missions may bring answers. Europa Clipper will fly through Europa's environment dozens of times, probing for plumes and analyzing chemistry. Dragonfly will hop across Titan's surface, searching for prebiotic chemistry. Mars sample return will bring rocks to Earth that may hold biosignatures. Proposed missions like the Enceladus Orbilander could directly test for life in geyser spray. We live in an extraordinary moment. Within a single human lifetime, we may confirm whether life exists elsewhere in our solar system. What it means to find life. If we find microbes in Europa's ocean, or Titan's lakes, or Mars's rocks, the implications will ripple across every field of thought. It would mean life is not unique. It would mean the universe is fertile, its chemistry destined to bloom. And if life can emerge multiple times here, then across the galaxy, it must be common. If, on the other hand, we find no life, if oceans exist but are sterile, that too is profound. It would mean that habitability is common, but genesis is rare. Life may require not just ingredients but extraordinary luck. In that case, Earth's biosphere would be even more precious. A rare jewel in a vast desert. Either outcome deepens our understanding of who we are. Alien oceans are not fantasy. They are real, mapped by spacecraft, measured in gravity fields, glimpsed in geysers, seen in methane seas. They are the hidden stage on which life may already exist, waiting for us to discover it. The solar system, once thought barren, is alive with possibility. We stand at the threshold of discovery with missions poised to dip into Plumes, to fly over lakes, to return samples to Earth. In our lifetime, we may know whether we are truly alone or part of a larger cosmic story. The oceans of Europa, Enceladus, Titan, Mars, and the Comets are calling. They whisper of chemistry and possibility, of life in darkness, of strange metabolisms and ancient fossils. To answer them is not only to search for aliens, but to understand ourselves. For the story of alien oceans is also the story of our own beginnings. One day, when future explorers sail on a submarine through Europa's sea, or fly Dragonfly over Titan's dunes, or hold in their hands a Martian rock containing a fossil, we will remember this moment, when oceans were still only whispers and promises. And we will know the solar system was never empty. It was always alive with oceans. We only had to learn how to listen,